Go ahead.
Axel gave me exactly 3 minutes to prepare a welcome, but I mean that's rather easy on the other hand. Welcome, it's a pleasure to see you. We moved, as you know, Nordita was moved to Stockholm in January. There are not that many people here, but one of those who are here is, of course, Axel, who has made a tremendous work on keeping activities up and organizing conferences. I'm very grateful for that. Thank you, Axel. And with this, it's really nice to see so many people here and see life in the house and things expanding. We are, of course, growing. I mean, in the fall there will come at least 5 more people here, 3 assistant professors and a number 5 postdocs, I think. So we are growing, but we are yet rather small, but it's coming along. And as I said, it's a pleasure to see all this activity. Thank you and welcome, and I hope you will have a nice time here in Stockholm.
Thank you, Ulf, and thanks to all of you for coming in such big numbers. So what I wanted to show you here is my presentation. Second. It's bizarre. Yes, here we go. So we are here in order to discuss progress with the pencil code. We had a meeting last time in 2006. The first meeting we had in 2005. That was a time when much of the work was really seriously reorganized, and that was also the time when the so-called equation of state branch was finally abandoned. This was one of the developments that led to a major disruption for a period of 1.5 years, and as I will discuss a little bit later. So the question is, what has happened over the years, and particularly also over the last few years. So I've prepared a few slides here in order to illustrate this. As you know, the pencil code is being delivered through CBS. That gives you up-to-date versions and revisions of the code, but there's also tarbos. And all of the old versions are still kept online, as you see here. The oldest version is 0.8 and had only a size of 377 kilobytes, and now has grown by a factor of 10 over the last 5 years. You also see here one major development, and that is related to a very unfortunate server crash that we had in Copenhagen, where the CVS repository is still located. So that led to the loss of information for the duration of 8 days. That was the latest backup that existed. And so that was extremely unfortunate and should really never happen again, of course. It's still located in Denmark, it's still not moved to Sweden yet. That will happen also at some point when everything's ready. In order to illustrate the progress over the last years, here a plot where I showed the increase in the number of nightly order tests that are being done. As you know, the code, of course, is being modified constantly by a number of people, and that means it needs to be checked constantly for its proper working. And there is now a suite of 25 test problems that are being executed every day and every night on 2 different machines. One is in Heidelberg and the other one is in Calgary. You see here that the number of order tests has grown roughly linearly over the years. That's perhaps good and natural, so we can expect that the pencil code, first of all, it's alive, it's a thing which is alive, it's developing, and it's growing linearly, and so is probably also the number of users, which indicates, of course, the increasing number of problems as well. Here, another interesting plot which shows you on the left-hand side the number of routines that the pencil code is working with. In the early years, we started with just some 20 different routines that the code was coming with. That was very easy to visualize. And we thought it's best to keep it like this. To hope that the number of routines is never really much bigger than a screen full of routines. And unfortunately, the number grew and grew and grew, and there's really no stop to this. It really continued to grow until the present day, linearly, approximately. And here you see this famous jump, which is just because of the fact that we did change the there was a branching of the code. As you know, in the CVS you can develop different branches. And that means you can decouple from the main branch and can, on your side branch, develop your own changes and will certainly not affect anybody in the main branch. At the same time, you can use all the developments that happen on the main branch and incorporate them back into your version of the branch. Or, likewise, you can move your developments on your side branch back to the main branch. And that's what happened in this case. And so here's only monitored the progress on the main branch. And so a lot of development happened for years, for 1.5 years on this side branch. And then at the first user meeting in 2005, these were merged together, and that led to this jump. Apart from this, there's still a linear increase. Also, the number of lines in the code is increasing. It's now 150,000 lines of code. In the early days, approximately 10 times less. Already a large number of lines of code, of course. As you know, there's a large number of people that are modifying and checking in the pencil code, modifications to the pencil code. This plot is up to date, but I should have done, as I realized, some further modifications to this. I started doing these kind of plots since 2005, and I have an automatic procedure to revise and update them. What we see here is a certain number of routines. There's, for example, one routine which is particularly strange, of course. There's a makefile, and then there's all of a sudden no change to the makefile anymore. That's because the makefile, of course, doesn't exist anymore. Wolfgang asked a very surprised question: how come we come to the code which doesn't have a makefile anymore? And that's, of course, because the code itself is making a makefile now. So so therefore, a makefile itself does not actually exist in the repository. There's only makefile.src, the source file is the makefile, which produces then the makefile. So therefore, this was makefile was abundant. Likewise, ionization, I realized, was abundant in late 2005. But that's because there's an ionization underscore temperature or something like this, which you are mostly working on. So ionization does not exist. Is that not right?
Well, it has been replaced by EOS underscore.
Yes, I see.
Something.
Right. Yes. So, for example, there's no equation of state at all yet, but of course, the equation of state does exist meanwhile. You see also then that certain other branches or subroutines come into play, like here, for example, Dust was developed first in 2003, and it's continued to be developed until the summer, for example. I have here also a list where we see the lines of code that are being modified. If you do the CVS annotate command on all the lines of Fortran code in the code. And I've not checked on all of these users, just a few of them, so this does not mean that there are not more users, there's a few more. I in particular looked into Steve, who just got online with developing his changes to the code since yesterday. And so already since yesterday, he managed to put in another 600 lines of code, of course. A number of changes comes from this really stupid EOS merger event, which comes from this remerging of the EOS side branch.
I think one issue here is that if you change the indentation or the key of the code, the line will be on the new afterwards.
That's
also
also
the reason why I have something.
Yeah.
Yeah.
So that's maybe it's a better way of doing that, of course, a more accurate way of doing it. Good idea. We also have, of course, made progress in running not only on faster machines, also on bigger machines. The largest scaling that is on this plot still is up to a number of 512 processors. That's the low-heat machine in Finland. And it shows perfectly linear scaling here. And the other change is the Baghdad cluster in Freiburg.
It's now called Damascus, but
it's still called Damascus. You also will have a Taliban.
We just follow some rules. For
We started with Kabul, actually.
Oh, yes. There's no Taliban. There's a restaurant called Taliban. So anyway, so that also shows perfectly linear scaling up to the last number, which probably have some good excuse for. But also, of course, the machines to become faster. So the lines, the time it takes, the number of microseconds per time second per mesh point does decrease even for the same number of processors on a comparable test problem all the time. So that's also good. And now just a few thoughts about the science. There's really not anything bigger yet as far as this 512 processor run at a resolution of 1024. I don't think so. That was done by Niels Haugen back in 2003. And although the code is in principle capable of running on, I mean, they should be soon able to run 2024 cube. Nobody has done that yet. And the largest MHD run that has been done in the world is actually now 1,586 or whatever it is. That's done in Boulder. So our run used to be the biggest one until 2005 or something, and then now it was superseded by the Boulder people for MHD. In Hydro, of course, there's a much bigger run on the Earth simulator. So we hope that this can be increased. One way to do that, of course, is to go to much larger number of processors. I will talk about this on the last day. One important development in order to be able to run, for example, on the new generation of machines, which include a number of processors between 80,000 and 800,000 processors, is that we need to parallelize in the X direction. This project has now started as well. One of the surprises that really is now firm is the fact that there is a bottleneck in turbulence. This was something which was really unclear at moderate resolutions and is now extremely clear since the 4096 cube simulation of Canida in 2003 for just pure hydroturbulence. So there is a Kolmogorov spectrum, E of k compensated by k to the 5/3 power, gives you a strong departure of 0.1 to the main power spectrum slope of 1.67, another 0.1 correction, and then just before the energy dissipates into heat, the energy per wave number level piles up. It's called the bottleneck effect. And so this is something one begins to see at large resolutions. And I think here's another animation here which shows you shock turbulence. So the code comes with a lot of different modules. Not everything is working with is a direct simulation. This is the simulation with shock viscosity included. It's a Mach number 10 simulation. And this is one of the shearing box simulations, but the right one is 512 cube simulation, also already fairly old, but that's how these simulations look like. And I think that's all I have here. So the code is still developing further, and these are just a few of the plots. Of course, there are many of the presentation, in particular Anders, whom I'm giving the word to now, who has, of course, many more recent developments undertaken with the principle. So with those few words, let me start then the meeting and give the word over to Anders.